The fire built a thunderstorm. The storm threw lightning beyond the flames. And new fires started where those bolts hit. That chain unfolded this summer in southwestern France. The wildfire raised more than a tall smoke column. It became a real storm cloud, carrying water, ice, and electrical charge. Then came lightning and violent winds that could suddenly turn the fire front. It is almost a closed loop. Fire lifts a cloud, the cloud makes lightning, and the lightning can make more fire. But why does this happen only sometimes? Two enormous fires can launch similar smoke towers. One falls apart. The other becomes a pyrocumulonimbus, a thunderstorm first pushed upward by the fire below. What has to line up in the sky? Where does ice come from above a blaze? And why can thousands of flashes still fail to tell us where the next fire will start? We will follow the chain from heat on the ground to a discharge in the sky. Then we will see why scientists fly above these clouds and through their smoke, and what they still cannot predict. Start before there is any storm at all. There is only intensely heated ground, flame, smoke, and air racing upward. Picture a gigantic chimney without walls. Fire heats the air until it rises, dragging smoke, ash, and surrounding air with it. The stronger the flow, the higher the dark tower can grow. But height alone proves nothing. As the air climbs into lower pressure, it expands and cools. If the plume contains enough moisture, invisible water vapor condenses into droplets. A column of smoke begins turning into a cloud. Then the atmosphere presses a hidden accelerator. Condensate vapor releases heat, helping the current climb farther. The cloud creates nothing from nowhere. It releases energy the water stored during evaporation. Higher up, droplets freeze. Ice particles collide in the turbulent flow and separate electrical charge. One region builds one sign, another the opposite. Tension rises until the air can no longer contain it. Lightning breaks through. That is why the phrase fire cloud can mislead you. Flames are not flying around overhead. This is a genuine thunderstorm system made of water, ice, smoke, and ash. Fire starts the climb, but the atmosphere takes over from there. Lightning is only one threat. Air racing upward must come down. Powerful downdrafts can hit the ground, spread outward, and change the fire's speed and direction within minutes. A familiar front can suddenly behave like a different fire. The column can carry burning embers far ahead, starting spot fires before the main flames arrive. A lightning strike into dry vegetation beyond the perimeter creates another route forward. Investigators connected exactly that chain to the French case. The danger is no longer confined to the flames you can see. It can arrive from above, from the side, or ahead. If you enjoy stories where nature breaks our familiar picture of the world, subscribe. Now the hardest question, why does this chain not start every time? It is tempting to search for one magic threshold. Make a fire hotter than this number, and a thunderstorm appears. But there is no reliable switch like that. The fire matters, yet so does the entire structure of the atmosphere above it. Near the ground, the system needs a powerful, sustained rise of hot air. Higher up, it needs an environment cool and moist enough for that flow to keep growing instead of collapsing. The moisture also has to be available where cooling can turn it into droplets. That is why similar fires can get very different skies. Even after a pyrocumulonimbus forms, it does not follow one script. One produces intense lightning, another produces little or almost none. One slams strong winds back to the ground. Another mainly carries smoke upward. The largest systems can inject material into the upper troposphere and even push some into the stratosphere. Now consider a number that is easy to misunderstand. In a cloud above Canadian wildfires studied in 2021, researchers counted about 5,600 flashes in only 5 hours. That sounds as if the ground should have been igniting non-stop. But many of those discharges stayed inside the cloud. For new fire risk, the total flash count is not enough. We need to know whether a bolt reached the ground, how much energy it carried, where it landed, and how smoke changed the electrical process. So a lightning counter is not a fire counter. A huge number tells us the cloud became electrically active. It does not hand us a map of future ignitions. This is where the spectacular observation ends and the difficult forecasting begins. To close that gap, the Earth Atmosphere Campaign INSPIRE is working this summer with NASA and other research teams. One high-altitude aircraft passes above these systems and studies them remotely. Another flies through smoke plumes, collecting samples and measuring conditions directly. Ground crews add radar and laser-based observations. Why so many viewpoints? Because an instrument above the cloud sees something different from an aircraft inside the plume. Ground radar adds a continuous view from below. No single measurement can capture the whole system, so researchers have to assemble the pieces like a three-dimensional puzzle. The campaign is still underway. The honest answer is not that scientists have already found a finished formula. They are collecting the measurements a useful formula would need. One central question remains: why do some fire-driven storms become wildly electrical, while others of similar scale produce very little lightning? And even predicting the cloud itself would not finish the job. The next step is knowing which discharges will reach the ground, where dry fuel will be waiting, and whether a strike will become a new ignition. There is still a large distance between we see a dangerous system and we know where the next fire will begin. Now return to the French wildfire. Heat alone did not manufacture a thunderstorm. An entire chain had to lock into place: a strong updraft, cooling, moisture, condensation, ice, charge separation, and only then, lightning. Fire delivered the first push, but it was never the only force. That is why a pyrocumulonimbus is both dangerous and difficult to forecast. It turns a fire from an event on the ground into a coupled system, linking the ground and the sky. Once that loop closes, fire can gain a fresh start far ahead of its visible front. Which frightens you more, the wall of flame you can see, or the storm above it, whose behavior scientists still cannot predict precisely? Tell us in the comments. And remember the key difference: seeing the cloud does not yet mean knowing where the next fire will start.